Welcome. My name is Norman Wagner. I am a professor in the Department of Chemical and Biomolecular Engineering, and I'm at the University of Delaware, and I'm the director of the Center for Neutron Science. Today, we're going to talk about Rheo-SANS. In your course, over the course of this fall semester, you've learned a lot about neutron scattering and soft materials. And today we're going to take that knowledge and push it a little bit out of equilibrium. So that's the framework for what we're going to do. I'll show you a brief outline, but I want to mention many people have contributed to the work. And most of the work has been pioneered by work done at NIST, at the National Institute of Standards and Technology, as well as the Institut Rheological in Grenoble, France. Some of the people here on the left have played an important role in the development of the instrument and the techniques. And during the course of this lecture, I will show you some instrumentation, give you some literature, and some of the slides I'll go through rather quickly because they're rather detailed technical drawings in that. They're there for reference. I also have some references along the way to some literature that can help you if you're interested in doing Rheo-SANS experiments, including a movie that's being produced about the method if you want to do certain experiments. And finally, we'll take questions along the way. I'll stop at various points during the talk and take questions, but feel free to type them into the chat. So here's a quick outline of the course. I'll try to motivate some Rheo-SANS. I'll give you a short introduction to rheology, talk a little bit about the instrumentation, talk about the stress SANS rule, and then give you a few examples. So why do Rheo-SANS? Well, you know from your course that neutron scattering can give you important structural information, especially on complex fluids and soft materials. From size ranges from the atomistic up to microns, maybe even 5 to 10 microns if you use USANS. And many materials have their properties because of the processing or are used during processing. And so we want to know more about the structure, not just the structure at rest, but also the structure under flow or other deformation conditions. There are also ways of using that structural information to access rheological properties that are not easy to measure in a mechanical rheometer. And of course, with SANS, one can start doing very intricate experiments where you can probe different components in a mixture. One of the advantages that you've learned about, namely contrast matching. This is the typical kinds of information that you get in Rheo-SANS or flow SANS. This is a worm-like Micelle, and we'll talk more about this particular pattern. But you can imagine that this is a very rich information, and the orientation of this pattern is actually related to the orientation of the molecular self-assembled structure under flow. It's this type of interesting pattern which gets us excited about doing Rheo-SANS as opposed to just equilibrium measurements. One of the first references I want to point out is a very recent review article by two of the people that I mentioned as co-authors on this work. Aaron Eberle, who's now a scientist at ExxonMobil Engineering, and Lionel Procard, who runs D22, the beamline at ILL Grenoble. This is in Current Opinion, and it has a very short article of a couple of pages, but it has 180 some references about Rheo-SANS work and published just in the last few years. So if you haven't thought about this field, you might find that there are quite a few people involved in doing neutron scattering under flow. There are many systems, and hopefully everyone in the audience recognizes a system that they're interested in on the list here, and this is by no means comprehensive, but you can see that whether you're talking about polymers or you're talking about colloids, self-assembled emulsions, surfactants, gels, clays, block copolymers, and more recently there's been a lot of work on proteins and biopharmaceuticals. You can imagine that Rheo-SANS is actually very interesting for people in industry, not just academia, and is a skill set that's in demand these days. At the very end of the talk, if there's time, I'll introduce you to a program called NSOFT for industrial users. If we have any attendees or course members who are in industry, it's an opportunity to take advantage of what I've showed you here today. In the review article by Eberle and Porcar, they highlight a number of flow geometries that one can use for scattering measurements. And in particular, today we'll be very focused on this 1-2 flow geometry as being a very important one. And if there's time, I'm not sure there will be, but I have some slides on extensional or cross flows. But people have used all of these different geometries to study various flow types that are important to understand material dynamics, as well as might be important in the processing of complex fluids. I'm particularly interested in surfactants and colloids and polymers. And if you just step back for a minute and look at a typical phase diagram for surfactants, this is SDS and water with oil. You can see a very rich phase behavior going from simple micelles in the lower corner here. And we'll talk a little bit today about rod-like micelles. But you can imagine some of these cubic phases and multilamellar vesicle phases we've studied with Rheo-SANS as well. Some of these phases are only formed by shear rate. They may not be equilibrium phases. Other structures, such as this bicontinuous phase, may not be able to shear. It might have to rearrange and flow by rearranging into a different self-assembled structure. So now you can imagine if you have this rich topology at equilibrium, if you start to deform it with increasing shear rate or shear stress, and maybe time-dependent deformations we'll talk about, you can get some very rich behavior, complex rheology that's connected back to changes in the structure. And Rheo-SANS gives you access to that information so you can better understand your system. So I'm going to spend a few slides about rheology because I realize that that really hasn't been covered in this class, but a number of the speakers before have alluded to it. For those of you who are interested in rheology, or maybe don't even know what it means, according to the Oxford English Dictionary, it's the branch of physics that deals with the deformation and flow of matter, especially the non-Newtonian flow of liquids and plastic flow of solids. There is a Society of Rheology here in the United States, which runs national meetings and short courses, and its motto is Panta Rhe, which is everything flows. And so whether you're talking about geological timescales over millions of years or nanoseconds associated with ballistic impacts of micrometeorites, it's all rheology. So in terms of some rheological concepts, we'll talk about simple shear flow. And I won't belabor the point. These slides I'll go through fairly quickly. They're really designed more for reference for later on. But if we talk about a simple shear flow, if we have two plates and we take this upper plate shown here and we slide it from left to right with some velocity, that would set up a simple linear shear flow if we're in low Reynolds number, right? So non-inertial flows. And we can define the shear rate, which is the symbol down here, as simply being related to the derivative of the velocity in the x direction with the y, or the gradient direction. And associated with those kinematics are dynamics. We can define a stress tensor. The components of the stress tensor include the shear stress, which is the one I'll focus on here. And that is essentially the force required to drive the plate in the x direction. Okay? As simple as that. The relationship then between the shear stress and the shear rate is the viscosity, and I'll show you that on the next slide. One could also talk about normal stress differences. These are important material properties for understanding, for example, polymer processing. And normal stresses can be positive or negative, and they can have important impacts on lubrication flows, as well as the processing of polymers. And they're defined there as differences in the stress tensor along the flow direction, for example, as compared to the gradient direction. So in terms of things, we have forces, stresses, which are force per area. We have shear rates, which is the velocity gradient. The viscosity, which is the ratio of these two quantities. And for Newtonian fluid, which we're all familiar with water, for example, at the typical shear rates we're interested in, the ratio is constant. So let me tell you a little bit about other flow types. We'll talk about extensional or elongational flows. These are stretching flows that you would find, for example, in fiber spinning. where the fluid elements are increasing their velocity. If you take a look at the center line here of the flow, the fluid is moving more quickly as it moves along the fiber draw direction, if you will. And we can define an extensional viscosity, which for a Newtonian fluid is just 3 times the shear viscosity. But for polymers, it can be much larger because they can strain hard. And I think all of you are familiar with viscosity, but just so you know, the dynamical range over the properties that we're talking about can go from molten glass, which is on the order of 10 to the 12th Pascal seconds, down to water, which is a millipascal second or a centipoise, and air, which is even lower than that. So we have a large dynamical range. Of course, not all of these materials can be put into our Rheo-SANS equipment, right? And the shear rates are also relevant. So if you talk about slow geological type of rates, such as sedimentation, mud in the bottom of an estuary, if you're chewing gum, if you're spraying or brushing paint, if you're coating paper, right? These, again, range over 12 orders of magnitude. And so we're not going to be able to access all of these shear rates with one instrument. Finally, I'll just talk briefly about some typical rheological models that you've seen. And what's being plotted here is the shear stress against the shear rate. The Newtonian fluid is just a straight line. The shear thinning material starts off with a large viscosity and later on a smaller viscosity because the slope goes down of this curve. The shear thickening fluid starts out with a lower viscosity and becomes very stiff, higher viscosity at high shear rates. And often, for many systems, there's a plateau limiting shear rate at low shear rates, another plateau limiting shear rate at high shear rate, and some shear thinning in between, and a characteristic shear rate that's important for us to understand. And so we would imagine that if we're thinking about structural deformation, here we have a structure that's close to equilibrium. Here we have a structure that will be deformed by the flow. And here we have a structure that is a very high shear structure, maybe very, very different than the equilibrium structure that corresponds to this viscosity. We will also talk briefly about viscoelastic measurements, where we do a deformation that's time dependent. The most common one is to apply a sinusoidal deformation in the strain, which means that the shear rate is a cosine. And we can define the stress also as being an in-phase and an out-of-phase component. That's shown here in the diagram. And the in-phase component with the strain is the elastic part, or G prime, the elastic modulus, and the out-of-phase component is the loss modulus. So we can get additional information by oscillating, if you will, the sample and measuring its response. Newtonian fluid will be in phase with the strain rate. A perfect Hookean solid will be in phase with the strain. Again, I realize I'm covering a lot of things quickly. Some of you will be familiar with them, some of you will not, but they're here for reference. And of course, many of the phenomena that we talk about in complex fluids can be thought of in terms of simple models for the rheology, simple mechanical models. I won't belabor the point here. This is, again, just for reference, but the simple Maxwell model you probably heard of, where we have a viscous element, which is a dashpot, parallel with a spring. And on the next slide, that gives rise to a typical spectrum that we see, where we plot these elastic modulus, which is shown here in the black, the viscous modulus, which is shown here in the red, as a function of the frequency with which we do the deformation. And here we're assuming that we're in the low amplitude limit so that the deformation is linear, that we're not far from equilibrium. This crossover point here, where G prime and G double prime cross over, is very important because that gives us the time scale for the material. This is essentially 1 over the relaxation time of the material. And finally, I just want to mention that the way in which rheology is done, which is relevant for doing Rheo-SANS measurements, we can typically use a rotational device, although we can also push fluids through a pipe, as I showed you also with the cross-slot flow material device that we talked about earlier. But the most common devices are, for example, a Couette device where one rotates the inner cylinder and the fluid is in between confined there. And I'll show you some of those later. Cone plate, which has the advantage of having a constant shear rate throughout the gap. And the easiest geometry to use, but not necessarily the easiest to interpret the data from, is a parallel plate or parallel disc geometry. So these are typically what's seen in a rotational rheometer in a laboratory, and are typical geometries that are used for Rheo-SANS, for driving the flow field. My last slide on rheology. Those of you who don't like tensors, I apologize. We went through a lot of material quickly. But if you're interested, there's some very good books on rheology. The one we particularly like to use here at Delaware, McCosco's book, Morrison's book. There's Tanner's book. On complex fluids, you'll find a very good book that sort of has chapters on all sorts of different complex fluids by Ron Larson. And I'll put in a plug if you're particularly interested in colloidal suspension rheology. There now is a book on that. Okay, I have just a few summary slides on neutron scattering. So if you wanted to check your email on your iPhone or something like that, now's a good time because you should know this. But it's important that we recognize what it is we're trying to measure with Rheo-SANS. So, of course, you know about small angle neutron scattering, and I won't belabor this point. But what does SANS measure? So for a particulate system, such as a paint or a toothpaste or a clay, you can imagine that you have scattering that comes from a form factor, which corresponds to the shape and size and polydispersity of the particles. And as you've seen, then a structure factor, which corresponds to the autocorrelation function of the positional correlation of those particles. So if I start with a dispersion of the red particles in the blue liquid, the scattering can be thought of as a convolution of the shape of the particles, size, shape, polydispersity, with their structural arrangement in equilibrium in the suspension. So I know we've covered that, or has been covered earlier in the semester. So my composite scattering, and I'm looking just here at a I versus Q plot, a one-dimensional plot, for such a colloidal suspension of spheres, would typically show the form factor of the sphere, which if you remember back to earlier in the semester you saw, times the structure factor of the arrangement of spheres in space. So this is the Fourier transform, direct Fourier transform of the G of R, the pair distribution function. And this is the autocorrelation function of the Patterson function, or the scattering function for the spherical object. So here's an example where we go to a dilute suspension. This is a picture of TEM of the particles that we're scattering from. These are colloidal silica on the order of 100 nanometers. And our scattering equation, again, I didn't talk about the prefactors, but you should know what they are by now. And for a dilute system, the structure factor is 1. So I'm left with the form factor. And that's a typical form factor giving the size, shape, and polydispersity. If I increase the concentration, I have structural effects. And as I increase the concentration, you can see that I get very interesting effects at low Q, which are associated with that structural term, the arrangement of the particles. Now, if I apply shear flow, it's important to recognize that the shear field breaks the symmetry of the system. And I have 3 planes of flow that I can access. And I'm going to show this in much more detail a little later on, so I won't belabor the point here. But you can see that the orientation of a Couette geometry, for example, looking from the top, where the neutrons are coming from here and scattering onto a 2-dimensional detector, I can go through the center of the cell, I can go through the edge of the cell, and I can tip the cell on its side, and we'll come back to looking at this in much more detail. The shape of the particles is generally not changing unless I have emulsions or soft particles. But for hard spheres, for example, that shape doesn't change. But what will change is the radial distribution function under flow. It will not be the equilibrium one. And so it's that structure factor that we're measuring in Rheo-SANS generally. So here's a better artistic depiction of what is actually happening in the experiment. So I have oriented things in such a way that we keep the shear cell fixed and we look at the neutron line changing. But of course, that's not how the world works, right? So our neutron reactor or spallation source is fixed, and we have to change or tip the rheological tooling. But this gives you an idea. So if I take a Couette geometry shown here, the sample sits in between the 2 cylinders. I rotate the inner cylinder. I can pass the neutrons down directly down the axis, or orthogonal to the shear axis, in the so-called radial configuration. What's depicted here in these pictures are ellipsoidal particles that are flowing along, and that's sort of what we would be looking at. If we go off to the edge, the tangential direction, we can look down the shear direction, and we would actually see spherical-like objects because the ellipsoids are oriented along the flow direction, and so we're looking down that direction, so we wouldn't see the long axis of the ellipsoids, we would see their cross-section. But most importantly for what we're doing today, we need to access the so-called 1-2, or the velocity-velocity gradient plane. That's where generally all the action is. That's where the anisotropy will show up under flow, and flow will show up. And I'll show you examples of that as we go along, and we're going to talk about this in more detail. But this is just to give you an orientation that under flow, even under simple shear flow, we have three basic patterns that we would like to collect to fully understand the structure under flow. Okay, so I'm going to take a step back to real optics, which is very well established in the literature. This is flow dichroism and birefringence. It's a fairly standard technique that you can find for measuring polymer orientation under flow. And there are literally thousands of papers published on that, and many commercial instruments over the years have been built. And so for polymers, if you think about putting a polymer chain under flow, I've shown that the coil, which should be, now you know from earlier lectures about polymers, is a random coil, will now stretch, will be an end-to-end vector. The stress is the dyadic product of that end-to-end vector, and that's Kramer's stress relationship, averaged, and the angle brackets mean ensemble averaged. The birefringence, which is the difference in the transmission of polarized light, where the polarization is along one direction versus an orthogonal direction, is proportional also to the stretching of the chain. The polymer chain will be birefringent. And if I stretch it, it won't be isotropic, essentially forming a polarizer, if you will, due to the flow. Since both of those are proportional to the same quantity, I can actually measure that stress, the polymer contribution to the stress, by measuring the birefringence, and the coefficient, which is tabulated in the polymer handbook for many polymers and solvents, is known. Now for colloids, and there's a reference for colloids down here, the difference is a little bit different. The difference is that we're not deforming the particles, we're changing the probability of finding particles relative to each other. That is, the shear flow doesn't change the shape of the particles, it changes their position in space relative to each other. And so we might imagine under shear flow we'll orient or change the neighbor distribution. That neighbor distribution is again characterized by a vector, and the component of the stress due to interparticle interactions is again proportional to the dyadic product of this. For colloids, we often don't use the birefringence, we use the dichroism, which is the difference in polarized scattering in two polarization directions, but it's analogous to the birefringence. Okay, it's the other component of the optical tensor, and we can once again write a stress that's proportional to that dichroism, and the coefficient is a stress optical coefficient for colloidal particles. And again, there's a reference shown here deriving that. Okay, so if we do scattering from colloids or surfactants, then we should think a little bit about what it is we're measuring. So for colloids, I already introduced the idea that we're measuring the structure factor. That structure factor will tell us the difference in scattering. That's related to the stress, and we'll see a stress optical rule, or a stress SANS rule, I'm sorry, the analog of the stress optical rule for neutron scattering. Let's go back to polymers and talk about that for a minute. And in fact, I'm going to talk about polymer-like micelles, or worm-like micelles. They're essentially living polymers, but you can think of them as long thread-like polymers. I think you've seen earlier in the semester the form factor for such a rod-like polymer or a worm-like polymer. There's a low Q asymptote, which tells me the length of the chain. There's a fractal regime with a Q to the -1 slope. That's characteristic of the rigidity, the segmental structure of the chain. And then, of course, we get to the molecular, or the diameter, if you will, of the micelles at high Q. SANS covers that range for worm-like micelles of the segmental shape down to the micellar diameter. Often we have to go to light or use SANS to actually see the length. These can be of the order of 10 or larger in terms of microns in length. Okay, this is a busy slide, but I'll walk you through it. The idea is similar to that stress optic law that I showed you before. I've changed nomenclature on you a little bit. Q is the analog of R. It's the end-to-end vector. For a polymer, we could represent the polymer, if you will, or this worm-like chain, as essentially a dumbbell connected by springs. Okay? And so Q gives me the orientation of that in the flow field. The stress due to stretching of the worm-like micelle or the polymer chain by the flow is directly proportional to this dyadic product of the Q vector. And that comes again from the same physics that I showed you before. And we can define an ordered tensor for that object, which is a normalized version of this Q to Q vector. So it's a normalized one. And if I were to plot this, what this tensor looks like, its surfaces, if you will, of constant value, would trace out an ellipsoid with 3 different axes, K1, K2, and K3, that tell me the net orientation of these. So imagine I now have hundreds of these chains, or thousands, or millions, or 10 to the 21, a whole or so, 10 to the 26 of these chains in flow. And I could ask, what's the probability of finding this Q vector, if you will, and that would trace out this surface shown here, for example. There are 2 very important scalar parameters that come out of this analysis, which will be essentially what we're going to measure in neutron scattering. So if I take this shape and I look at a projection of it in the 1-3 plane, if you will, or the 1-2 plane, I can define a characteristic angle, theta naught, which tells me how these chains on average are tipped relative to the flow direction. And I can define an alignment factor, which tells me essentially the sharpness of the distribution. Okay, so as I have a greater degree of alignment, I head towards a pneumatic-like system, which would be almost like a pencil-like ellipsoid, very strongly aligned along, for example, the flow direction. And typical derivations of this you'll find in Giesecke's original paper, and a paper by Matt Helgeson, who's now at the University of Santa Barbara, on that more recently. So when all is said and done, one can relate this alignment factor and orientation angle to the shear stress that we would measure, for example, in the rheometer by the elastic modulus and a coefficient, which is our stress SANS coefficient. So this becomes a stress SANS rule for polymers. And if I measure the alignment factor and I measure the angle, okay, then I can also calculate a normal stress difference. For example, in the 1-2 plane, I get N1. Okay, so I get some information then from the neutron scattering about the structure under flow for these polymer chains or worm-like micelles, which I can directly convert to rheological data to within a constant, which often we calibrate by comparing 1 point of the rheology to 1 point of the structure measurement. Okay. So how do I get that information from neutron scattering? I'll show you the instrumentation in a little bit, and we'll take a break for questions in a minute. But let's just go over how we get that. So remember our chain, which I show here, being this comprised of surfactant molecules, or you can think of it as just a native polymer chain if you like, has a segment, has rigidity over a segmental length, a Kuhn length, if you will. At equilibrium, I'll have a network of these objects, and it will be randomly oriented. Segments will be randomly oriented. And therefore, my neutron scattering will show a characteristic isotropic pattern. In this case, there's a ring because these worm-like micelles might be charged and they repel each other. So there's some preferred distance. Under flow, I will orient these chains, preferentially, for example, along the flow direction. That's one option. And if I do, the ring will turn into something that has maxima and minima in it. The maxima here correspond, as you know, from the reciprocal relation of scattering to objects aligned along the vertical axis, because the scattering is more intense than the horizontal axis. That 90-degree shift is due to the reciprocal relationship between real space structures and scattering structures, as you learned earlier this semester. You can see that these are not perfectly flow aligned because the angle primary axis or principal axis of the scattering is not exactly at 0, if you will, or 90 degrees relative to the flow, and that defines some characteristic angle. To calculate the degree of alignment, the sharpness, if you will, of that deformation, we use a technique borrowed from X-ray scattering and work done by Lynn Walker, who's now at Carnegie Mellon many years ago, published in Macromolecules, where we can trace, pick a particular Q vector. For example, we might be interested in the nearest neighbor kind of distance, so around the peak. And we trace that out as a function of angle here, and we fit it essentially to a cosine 2 theta function. And you can do that by either fitting that function, or you can do this integration here and normalize it. And that number gives you the alignment factor. Now, our choices for alignment factor are easy. For an isotropic pattern, this integral is 0, so we get 0. For perfect alignment, which this is not perfect alignment, but if we had perfect alignment, we would get an alignment factor of 1, the way this is defined. You can also get an alignment factor of -0.5, which would be if your material tipped orthogonal to the flow. So instead of flow aligning, like shown here, it would be 90 degrees to the flow. You can get that with discotic clays and things like that. So our alignment factor can range essentially from 0 to 1 for most materials, but it can be negative for some specific materials like clays, which might organize in various different ways. Now, coming back to the suspensions, the derivation of this is more involved than we have time to cover, but the basic idea is to take that structure factor, which is no longer isotropic, right, and to expand it in some basis set to work with. And the easiest thing to do is to use the spherical harmonics. So those of you who remember your freshman chemistry, your orbitals, right, and sort of the basic structure of quantum mechanics, you use these spherical harmonics, right, to represent orbitals and also to solve problems in quantum mechanics. We can do the same thing here. I've just shown you the 0th order harmonic here, which is isotropic. So at equilibrium, that's all you would have. But under flow, you'll distort the structures, we'll see. And so we can represent it as an infinite series of higher order harmonics. I've just shown you B22, B20, there's B40, B42, B44, et cetera, right, as far as you want to go. So the derivation of this is some work I did years ago with Bruce Ackerson, and that's published there if you want to take a look at it. What's important, though, is we can develop a stress-SANS rule for suspensions in much the same way we derive one for polymers. We expand the microstructure in these spherical harmonics. We write the stress in terms of the microstructure, substitute in the spherical harmonic expansion, and lo and behold, if you look at the math, which is shown down here in this paper, only a few terms survive in the stress expression. So you get a very simple relationship between the deformed structure factor, which you can analyze by doing a spherical harmonic decomposition of what you measure in the scattering, and which components show up in the stress expression. And so this helps, though, to have information in all 3 planes of flow again, because to reconstruct that spherical harmonic expansion, you really need information in all 3 planes of the flow. Okay, so I want to take a very short break, but be happy to answer any questions, because now I would like to show you a little bit about the actual sample environments that are used in neutron scattering, and then I'll show you a little bit of data. So any questions? I don't expect much, but if you have any questions, we'll take a short break. I don't see any questions coming, so that's good. And we'll stop again in another 20 minutes or so for more questions. So let's get started. The next 3 slides sort of give you this orientation a little bit better in terms of how we might probe scattering in a shear cell. This is sort of an artist's depiction of the shear cell developed originally by Peter Lindner, one of the first geometries. And I'll show you more schematics of it later. But it's basically a couette geometry. And you could think about, what if I had a lamellar surfactant flowing, which had periodicity, so stacked sheets, right? And what would I see, right, for different orientations? So if I do the radial experiment where I put the neutron beam through a gap, if you will, in the water bath that's controlling the temperature, rotating inner cylinder, an outer cylinder, and the sample somewhere in between here, the beam goes through in the center, so we're going down the gradient direction of the flow. And if we had oriented lamellar in this direction, by now you should recognize that that periodicity that you see here along the vertical axis would correspond to these Bragg peaks. If I had orientation in this direction, which is possible, not likely, but possible, then I would see these patterns, these Bragg peaks. And if I had the lamellar oriented along the flow direction, right, so curving along the cylinders, then I would see nothing. Because for the neutron scattering, I'm looking orthogonal to the direction of periodicity, the normal to it. And so there's nothing to diffract from, and I would see basically nothing. Right? So that gives you your first clue that you need more information, right, than just one geometry. The tangential beam, same exercise. I won't go through it in great detail, but now you can see if I go down the edge of the cylinder, now I'm looking in a way that I would see the lamellar in that geometry here, okay? If they were oriented in this way. I didn't see them in the radial, I see them in the tangential. And of course, the holy grail for many problems is to go down the gap, the so-called velocity gradient plane of flow. This, of course, is very useful for looking at these structures, not useful for looking at this structure. But for many of the materials, we're not interested in lamellars. We have other structures. The 1-2 plane of flow is very useful. That's not possible with this standard shear cell because we can't simply tip the neutron beam on its side. We don't have neutron mirrors, if you will, that we can reflect the beam through. And we're certainly not going to pick up a nuclear reactor and move it. Okay. We have to change the shear cell. I'll just show you, these are more for historical reference, but if you ever write papers about Rheo-SANS, you might sort of wonder who did these things first, or who came up with some of the early shear cells. Of course, the couette cell was developed by Couette himself, a French scientist in the late second half of the 1800s, okay, about 1880 or so. And his instrument is in existence in a museum in Paris. This geometry is based on that. So we have a rotating inner cylinder, a cup that this goes down into, and the sample is held here, alignment devices, and of course the neutron beam, right, coming through, giving you an idea what's going on there from a top view. Okay, and this was developed by Peter Lindner and was deployed at the ILL, Institut Langevin at Grenoble. Okay. About the same time, a Dutch group at Utrecht also built a shear cell. The advantage of their shear cell was that it was sealed. It had a different environmental control. This is taken from their paper back in 1988. This is the work of Kees de Cruyff and his students. And again, you have a couette geometry here, and the rest of this is alignment tools and motor drives with that. And again, the flow geometry, these were designed to do this sort of radial scattering. Okay, across the flow gradient direction. In the United States, shortly after Peter Lindner's design, a very similar design was built by essentially Strady and Hanley at NIST, also developed by Rexhelm at Los Alamos. And the design is very similar. Okay, you have a rotating device. Now notice in all of these designs, you're essentially driving the flow with a motor, so you're setting a shear rate, generally a constant shear rate in these instruments, and you're not measuring the stress, so you need to do the rheology offline. Okay. De Cruyff and Johnson, though, came up with a very clever design to try to access the other planes of flow. So Lindner's design would get you the radial and tangential. You couldn't get the 1-2 cell. But the 1-2 direction is the most interesting one, as I said. One way to get at that, not the best way, but one way to do it that's sort of clever, is to use a parallel plate device and rotate it relative to the neutron beam. Okay, so when it's perpendicular, you're essentially doing the same experiment as the radial in the couette. You're going down the gradient direction. But by rotating the plates, rotating the plates relative to the beamline, you can begin to access other information. It's not a clean measurement of the 1-2 plane, but it was the first attempt to do this, and they did that for essentially hard spheres and reported that data back in 1990, and those measurements were done in Grenoble. As far as I know, it was only done once. In the United States, then, there was a move to put a rheometer, essentially use a rheometer to drive the couette geometry, and that was done with a Bolin CSR rheometer originally, and that's shown here. And that was published you can now see about a decade later. And more recently, and what you will find on beamlines now around the world in many places, is based on work that Lionel Porcar and Paul Butler and a group from Par Physica, Anton Par now, did with Danilo Pozzo, who's a faculty member at Washington, and that's shown here in this review of scientific instruments, where they use a rather sophisticated rheometer and have a flow geometry with solvent traps and have slit geometries to look both at the radial and the tangential. That's the narrow slit here, if you will. Very clever and useful device where you can measure rheology simultaneous. So now you have access to what's going on in the rheometer as well as what's going on with the neutron line. Here's a picture of a modern device. Here's the quartz cell. You might be curious about the volume. A typical volume of this cell different cells can range from a few milliliters up to about 10 milliliters. If you're doing monoclonal antibodies, that's a lot of material. If you're doing colloids, that might not be a limiting feature. There is some attempt to have temperature control in this particular geometry, and that's air-driven couette kind of extra cylinders, if you will, which have air, which can be used to heat and cool the cell to some level with that. Again, I'll emphasize, though, that the couette geometry, if you look from the top, you have access to the radial and the tangential, and that can give you a lot of information. And what's shown over here are actual scattering patterns from a shearing Wormlike Micelles solution, and you can see it's highly flow aligned. But it's really going down the gradient if you are going down the 1-2 plane, the vorticity axis, so you access the flow gradient direction. That's very important. One reason that's particularly interesting for me and my research group is the fact that you can get shear banding flows, where the flow field is not homogeneous. It actually breaks into 2 or more different distinct flow regimes, and as I'll show you, you can access that information only in that 1-2 direction. The others average over the entire flow field. And as I showed you before, the idea that the pattern is very rich and can be used then to predict the rheological stresses, you really can't do that with these patterns up here. Again, we tip the couette cell on its side and we seal it, and I'll show you a picture of that next. Before I do, I would mention that people have accessed the 1-2 plane before, although they don't have the spatial resolution to look at shear banding. There's beautiful work done by Wes Burkhardt and co-workers using an annular ring cell. And this is X-ray scattering work. There are a number of papers on that. And there was actually an attempt to do something very similar by a French group, published at just around the late 90s, again using this ring-type geometry, bringing the neutron beam through, and trying to get access to this 1-2 plane. Okay, so our sample environment is a couette geometry that's sealed, turned on its side. There are windows for the neutrons to go through. And through the use of a slit, we can collimate and look at different parts of the flow field that's shown here. You can see the scattering transmission through the gap, if you will. Here's the team that did some of the original work that I'll show you a reference for the publication later. There's Lionel and Paul and Matt Liberatore is a faculty member now at Colorado School of Mines, and Florian Nettesheim, who works for the DuPont company doing neutron scattering. Here's a static scattering from 3 different cells, the standard rheometer that I showed you before, the 1,2 cell, and the usual static couette. And you can see the agreement's very good. One of the downsides of using this flow geometry, though, is that there's a finite path length. In this case, it was about 7 millimeters. We have 5 millimeters, but that can be fairly thick if you have high scattering. You could get multiple scattering effects. This is something to keep in mind. So we can then measure, if you will, either by using an open slit geometry. We get some sort of average pattern that's shown here. Here's our 1,2 plane data. Or we can use a narrow slit and scan it across here, okay? And if we do, for example, near the inner rotating wall, we might see high alignment. Near the outer wall, we might see very low alignment. Because the flow field is depicted in this cartoon, the local shear rates can be very different. Here's typical data that you would see with such a device, and I've reoriented things to make it easier to understand. So going from the bottom pattern to the top pattern, we're moving from the rotating inner cylinder to the outer cylinder, and here's our fluid, which is the blue, which is a worm-like micelle in this case. And you can see that at low nominal shear rates, it's fairly isotropic everywhere. And at very high shear rates, it's highly aligned everywhere. But somewhere in between, we have highly aligned regions coexisting with almost unaligned material on the outside. And that's a signature of shear banding. And this is the measured velocity profile, for example, for the 700 shear rate. It corresponds to the purple pattern here. Near the inner rotating wall, you have a very high shear rate. The slope of this is very large. The slope of this part of the flow is very small. The shear rate's lower. So that's typical data that we can extract from this instrument. This is all at steady state. I'll show you time-dependent data later. So if you want to learn more, again, I point you to this reference. Also, there was some highlighted data of time-dependent use of this instrument to look at large amplitude oscillatory shear in the Rheology Bulletin of the Society of Rheology, and a publication by Carlos Lopez Barron and others that I'll come back to on self-assembled block copolymers using time-dependent 1,3 scattering from the rheometer that was published in Physical Review Letters recently. And that's shown here a little bit more with the co-authors, where in fact we were able to create crystalline structures that were generated by shear flow. So if you're interested in shear-induced crystallization and shear melting, I would point you to this reference for some information about that. We did that both with steady shear and now more recently with dynamic shear. So let's talk about the time-resolved work. You know it takes, from your class, you know it takes time to collect a neutron scattering pattern. It could be 5 minutes for a worm-like micelle. It could be 30 minutes for some materials, depending on the strength of scattering. Just within the last few years, people have been doing time-resolved flow neutron scattering, or Rheo-SANS as well. Here's an example from the Paul Shear Institute. This is work of Simon Rogers, who's actually a postdoc with me now in my laboratory. But you can see here a worm-like micelle, which is oscillating. So here's one part of the oscillation. Here's another part of the oscillation where it's highly aligned. And one can map these out. So I point you to this reference to soft matter. Similarly, the idea is to do stroboscopic SANS. Okay? So our rheometer is now oscillating. This shows you the strain and the strain rate. And we start collecting patterns. And we either collect the time information, okay, so we do T-SANS, or we bin electronically, collecting neutrons only over, let's say, so many milliseconds, 10 milliseconds of time. And then we repeat this oscillation many, many times on the rheometer and with the neutron scattering. So let's say we collect 30 or 60 bins during one cycle, and we continue to loop until we collect in each bin about, let's say, 5 or 10 minutes of information. Hence, we get a good solid scattering pattern. Of course, this requires us to be in what's called an alternate state for the material. That is, every oscillation is the same, right? So when you start up, there might be a few oscillations before the material settles down into its stable, if you will, alternate state, that's called. So essentially, you're conducting 30 patterns. Now, we've now implemented this in the 1,2 shear cell, which is particularly powerful. This was done in 2011 at the ILL in in France, and we call this star sands, if you will, for spatio-temporal resolved sands, and this is now under flow. And here's the team, if you will, that implemented that. It was a rather heroic effort, getting everything to work. If you're interested in this technique, there is actually a journal called the Journal of Visualized Experiments, and the paper and the movie have been created, if you will. Kate Gernon, the graduate student you saw in the previous picture there, stars in the movie in which she implements the method at the NCNR at NIST, goes through the assembly and loading of the cell and the alignment and all of that. There's a paper and a movie that should appear probably in January in the Journal of Visualized Experiments. And so if you're interested, you can take a look. You can learn more about the experiment, and you can actually use that as a guide to actually performing the experiment with the assistance of people from the beamline scientists. I'll just put one slide out. This is from Dr. Katie Weigand, who was one of Danilo Pozzo's students, who's now a beamline scientist at NIST. And she's been developing advanced shear cells, or cells, I'm sorry, that measure extensional flow. And there's a history of essentially mapping out polymers under extensional flow. There was a nice paper in Science in 2003, and that's shown here, this particular flow. There's other work on polyethylenes during uniaxial drawing, so that's possible. And at NIST and other places, people have developed essentially these slot flow devices to generate extensional flow. So there are different ways to do it. And here are some references. This was work done at ISIS. Okay, so we'll take if there are any quick questions. Otherwise, I'll show you some examples of what you can do with the method. Okay. Let's take a look at a first example, which is probably not the one you would think of first, and that is immiscible polymer blends, shape and orientation. I'll tell you a little bit about colloidal aggregates, worm-like micelles, and then we'll cover snafu sands and a little on extensional flow if we have time. So if you take a polymer blend and you shear it, you'll disperse, under the right conditions, you can disperse the blend into droplets. In many materials, you would like to disperse this blend into the submicron or micron, let's say 10 micron or less size range. Under flow, these droplets will distort, orient, and you can measure that using neutron scattering. So this is some work done with the traditional kind of shear cell, not the 1,2 cell. And you can see highly anisotropic patterns here at different shear rates, with increasing shear rates, for a blend of two polymers in which we have contrast between them. And you can do the on-axis pattern, and which is shown here, this type of geometry. You can do the off-axis pattern, or the tangential, which is going down the shear gradient direction. And if you make an assumption that the droplets are roughly uniaxial, you can uniquely calculate the size and shape of the droplets because you know how much phase volume you have. And so you can actually get a plot of the aspect ratio, and the aspect ratio of the axes is actually related to the aspect ratio of the neutron scattering pattern, very trivially. And you can get the tilt angle, which is shown here, relative to the flow direction by essentially combining these two. Now, we'd like to measure the tilt angle, as I'll show you, directly in the 1,2 cell, but we didn't have that equipment back then to do this work. And you could take that information and you could compare that to different theories shown here for the equivalent radius, if you will, the drop as a function of the applied shear stress. And you can imagine if you're making a material and you care about the amount of interfacial area, for example, in toughening a polymer blend, or you want to create droplets of a certain size, this information is very valuable. And so there's a lot of information on the slide, but it's an example of how, if I go back, I can combine neutron scattering from two of the planes with an assumption about the droplets, and I can get information about their size, shape, and orientation relative to the flow. Okay, it's just simple geometry. That's probably the easiest one to understand in terms of a form factor, right, in the scattering here. We're sort of looking at individual droplets under flow. Colloidal agglomerates are quite interesting, and here we might be interested in the fractal dimension and the compaction. Here's a typical fumed silica aggregate. And this is some work that was done with DuPont and a group at Munich at the time, Wolfgang Peukert's group, and a graduate student, Mark Sommer. If I look at a scattering from such a fractal, if I combine light scattering or ultra small angle neutron scattering and small angle neutron scattering, I will get information about the fractal dimension here. The slope here is about -2. This is a colloidal aggregate made of Ludox, which we destabilize with salt, and that's done in D2O, and we wait a certain amount of time, and we get a certain size. For reference, the form factor of the sphere would look like this on the scale, and you can see out here we have obviously spheres, so the first minimum in the form factor, but the fact that they're aggregated shows up as this -1 slope here. Now that's at rest, and if we put it under flow, we can change that fractal dimension. So we're starting with this stable dispersion. I haven't shown you the scattering, but it would look like this. And with time, I'll grow some aggregate size. And at low Q, which in light scattering would show up, we can see the overall size of the aggregates. But what's important for us, perhaps, is this fractal dimension. So here's a plot now of that fractal dimension. So I've taken scattering data, and I haven't shown you the data, but I've taken and analyzed that fractal regime. And I've plotted that fractal dimension as a function of time after adding the salt, if you will. And I can do that at rest, and I can do that, I can do that at rest, which gives me a fractal dimension of around 2, but I could do that under shear. So this is the characteristic shear rate. G dot in this plot is gamma dot, is the shear rate, a very high shear rate. And you can see that the fractal dimension under flow that we reach at steady state is very closer to 3, which tells us that it's a very compact object, as opposed to the fractal dimensions we get under simple Brownian motion that we get from neutron scattering or light scattering or calculation. And that's a very open structure, okay, more like what you saw in the previous plot. So processing these colloidal fluids, the neutron scattering tells us immediately something about the density, if you will, of the aggregates that form due to shear. I can also do an experiment where I form the fractal aggregates quiescently, and then I turn on the shear flow. And I measure how the fractal aggregate compacts, if you will. And that's shown here. So as I increase the shear rate towards this 1,000, I change the fractal dimension, which means I go to a more compact object like this by increasing that. Okay. So again, neutron scattering here can be used to watch the restructuring, if you will, of these colloidal aggregates under flow. It can also give me the kinetics. If you look here, the fractal dimension grows much faster under flow than Brownian motion, and that's because at these high shear rates, we're bringing the particles together more quickly than Brownian motion. Okay, let's talk a little bit about surfactants. We have a few minutes. Okay, so I'm very interested in these shear banding worm-like micelles, and for technological and scientific reasons, the technology is really based on the fact that if I make a plot of the shear stress as a function of shear rate, remember for a Newtonian fluid, this would be linear, which is what we see at low shear rates, but at high shear rates, with very small changes in shear stress, we can jump orders of magnitude in shear rate. This is a breaking rheology that's useful to make these materials useful for consumer products like shampoos, as well as detergents and that, carriers for consumer products and medicines, but also as fluids used in the energy industry for oil recovery, tertiary oil recovery, and fracking. If I look at the, just do some optical microscopy and birefringence, I see that near the rotating inner cylinder, I see a very bright region, and near the outer cylinder, I see a dark region, telling me that there's different degrees of alignment. But I can't really quantify that very easily using birefringence. On the other hand, I can do velocimetry measurements by putting seed particles in. And I see near the rotating inner cylinder a very high velocity, and near the outer cylinder a very low velocity. So I have a shear banding flow. And so the flow out here is not homogeneous. And so we really need to look down the gradient direction, as I've shown you here in the 1,2 cell, to see what's going on. And so we've done that. This is just a plot of temperature versus surfactant concentration. And what's important here is that we're going to look at, in particular, at this state here in red, where we see shear banding like rheology. And this state is near to the isotropic nematic transition. So we have an isotropic state where the worm-like micelles are randomly oriented at rest. but we're not too far from the pneumatic state. And that's where we typically see this particular type of shear banding I'll show you. And just for completeness, of course, optically, the pneumatic state is birefringence, so you see beautiful colors on the cross polars. The isotropic state, you don't see anything. If I shear this fluid, I see at moderate shear rates a high shear band and a low shear band, right? You can see that the velocity field is not homogeneous. If I go to really low or really high shear rates, I see a homogeneous velocity field, right? What you would expect for a simple fluid. So I showed you this data before, so I won't spend much time on it, but now we can understand that the neutron scattering is telling me, for example, the degree of alignment relative to the flow, the orientation of the micelles, and the degree to which they're oriented. And that's changing as I go near the outer wall, right? Out here, I see a more isotropic pattern. Near the inner wall, I see a highly anisotropic pattern. And again, that corresponds to these velocity fields here. So we can bring all that information together using our stress-SANS rule. And there's a lot of data on this slide. And I just want to show you that you can get a lot of information out. You get patterns everywhere. You can analyze the angle. You can analyze the alignment as a function of position and as a function of nominal shear rate. Just focus on 700 reciprocal seconds, which is right here in the middle of the plateau. That is the purple curve here, okay? And you can see again near the rotating inner cylinder, the angle is very close to 0, which means that the segments are aligned with the flow direction. And near the outer cylinder, the segments are not aligned very much with the flow direction. And the strength of alignment, or the sharpness of the pattern, for the purple curve, you can see near the inner wall is very high. The number that we get is actually very close to a pneumatic. It actually is in the pneumatic region of what you would find for an equilibrium pneumatic. And far away near the outer wall, it's very low. Okay, so what we have is a highly flow-aligned state that's shown here in this pattern near the rotating inner cylinder, in equilibrium with an almost unaligned state near the outer region. Take that information for this state that I just showed you there, which corresponds to this velocity field, and I could calculate the angle now and the alignment factor as a function of the actual shear rate locally, because I have the local shear rates, which are the derivative of these plots over here, and I have the scattering that corresponds to those local shear rates now. And what we find is two things. One, a rheology model that fits the actual rheology fairly well, does an excellent job of predicting what we should see in the neutron scattering. So the line here is a prediction of the line from the rheology. So we measure the rheology, we predict what we see in the neutron scattering. And the blue points correspond to the isotropic state at low shear rates, and the red points correspond to the highly aligned paraneumatic state at high shear rates. And you can see very good agreement between the stresses and the neutron scattering measurements, which tells us that the stress-SANS rule, if you will, is holding it. Okay. And if I combine that information, I could plot the viscosity, if you will, due to polymer orientation as a function not of shear rate, but of the degree of alignment. And again, the blue points are in the isotropic phase, the red points are in the highly aligned state, and the line is the Giesecke model, rheology model for the fluid. And what it says is that this is just a continuous behavior, okay? We have two different types of states, but they're the same material. And they correspond to the same underlying structure of the material. Okay. So we can then create a non-equilibrium phase diagram. So if I go back to my temperature composition phase diagram, shear banding occurs near the isotropic pneumatic phase transition. If I now plot that this concentration axis and temperature axis can be collapsed down as essentially the distance from the pneumatic. So at any temperature, I can ask, if I have a state point, how far away am I from the pneumatic at the same temperature? That's plotted here. So 0 means I'm at the pneumatic phase, and positive numbers mean I'm in the pneumatic. Over here is a dimensionless shear rate, the so-called Weisenberg number, which is the shear rate times the relaxation time of the material. Anything inside this region is a two-phase material, okay? That is, it shear bands. And so I have a pneumatic or a paraneumatic in equilibrium with an isotropic phase. So we've measured that, and the points are shown here, and there's literature data. If you read the paper that's published in Soft Matter in 2009, you can get more information about that. So this becomes, if you will, a non-equilibrium phase diagram telling us when and where shear banding will occur. Okay. Now, we don't know the tie lines because we haven't measured the concentration yet. That's what I want to show you next in just a slide. And that's something which we call SNAFU-SANS, scanning narrow aperture flow ultra small angle neutron scattering. The publication is here by lead authors Matt Helgeson. And the basic idea is that the concentration locally, since we have local neutron scattering in the flow field, can be related to the transmission that we measure. But to measure that transmission, we really have to go to ultra small angle neutron scattering for a variety of interesting reasons associated with these materials. So we've done that, and I just summarized the data here. So there's a lot of data on the left. At low shear rates, the transmission as a function of position in the flow field is uniform. You can see that the black points here. And that just says that the composition at equilibrium is uniform. If we go to that 700 reciprocal seconds or 800 shear shown in green, we can see that we have a very low transmission at the inner cylinder and a high transmission at the outer cylinder. And that corresponds to a large jump, if you will, in concentration. So in the high shear regime, a low transmission means that we have a high concentration. And that's consistent with the idea of forming a pneumatic structure. That's in equilibrium with an isotropic structure, which must deplete and be at a lower concentration. So essentially, we've shear-induced an isotropic pneumatic phase transition, and it's not surprising. And theory would predict, by the way, some early work by Veronique Schmidt, summarized nicely by Cates and Fielding, and I can give you those references if you're interested, that we should have this phase transition. Of course, when we go to very high shear rates, everything has to come back. We have to conserve mass. And so we force the system to be a paraneumatic, but at an unhappy concentration. And for some systems, this leads to instabilities at these high shear rates. So SNAFU-SANS then allows us to essentially put the tie lines in the phase diagram. So we had these state points, and now we know that the paraneumatic is at a high concentration, and the isotropic phase that it's in equilibrium with is at a low concentration at a low shear rate, the paraneumatic at a high shear rate, and we now have the tie lines in between. So it's essentially a full non-equilibrium phase diagram. And again, you can read more about that in the papers that I've cited. Briefly, I'll just show you a slide or two. I realize we're pretty much out of time. Just a slide or two about extensional flow. As you change the flow rate, shown here, you get different degrees of orientation depending upon where you look in the flow direction. And so you can learn a lot essentially now about worm-like micelle or polymer alignment under flow. Okay, but now the flow is not trivially shear, it's extension, which is actually much stronger in alignment and much more relevance for some processing flows. You could calculate alignment factors, and that's shown here as a function of flow rate, looking at the center of the flow cell, and you can see the degree of alignment and the orientation angle relative to the flow that you can get this information. And again, if you're particularly interested in doing this experiment, I would point you towards Katie Wiegand, who's a staff scientist, beamline scientist working at the NCNR at NIST, and they have these flow geometries there. Here's just data showing you at different points in the flow field. You get, of course, different structures because you have the inlet flow and you have the extensional flow afterwards, and you can see the high degree of alignment. And remember your reciprocity relationship. So the scattering horizontal means that you've got the worm-like micelles aligned along the flow direction. And this, again, is for acetylpyridinium chloride, an entangled worm-like micelle system. So just to finish up, I think I've hopefully convinced you that Rheo-SANS, it's fun because you're getting now a lot of interesting information. You don't just have to settle for steady shear flow. You can do extensional flows. You can do true time-dependent flows. We've done large amplitude oscillatory shear flow. I can point you to some references for that if you're interested, or you can watch the movie of that being done by the Journal of Visualized Experiments. And this is instrumentation that I've shown you is actually quite widely available. At the NCNR at NIST in particular, and ILL Grenoble, all of the instruments that I've shown you are available. Of course, the Helmholtz Centrum at Berlin has a rheometer. Los Alamos has a flow cell. Oak Ridge is building Rheo-SANS. They have a rheometer. The Australian ANSO has a rheometer. China and other countries are building equipment as well. And if you need beam time using Rheo-SANS, you can apply for it. Right now, ILL and NIST have, you can apply for beam time to look at your sample. Finally, for those of you in industry, NIST has a special program called NSOFT, which has access to all of this rheometry things there. Point you to Ron Jones at NIST. Might be interesting for those of you, or if you're students and you go off in industry and want to do neutron scattering, there is an industrial consortium around that. And in particular, the types of things they're interested in are here. So I'm going to go back 2 slides to my conclusions. And thank you for your attention. I hope this was interesting. I realize this is towards the end of the semester. I'd be happy to answer any questions that you may have. Okay, I'm going to sign off now. Thank you again for your attention. I'm actually going to go teach my graduate class about Rheo-SANS as well, which takes place in about 10 minutes. So thank you. Have a good day.